Okay, the next problem I want to talk about is number 7. Part A simply asks for the definition of the derivative. So there are two answers that I thought that we've talked about in class that could be given. One of them I thought was the most likely one, and that's to say that f prime of 3 is the limit as h approaches 0. F of 3 plus h, we're plugging in x equals 3, minus f of 3 divided by h. Okay, that's what I was looking for. It doesn't ask you to do anything with it. It just says write it down. If you were inclined to use the other definition, we used it. I showed it once in class, and pretty much I showed that this is the same as it, and then we've always been working with that. But, maybe in high school your teacher wanted you to, or encouraged you to use the other one. So let me show you how that goes. Here's the other acceptable answer to part A, and that is f prime of 3 equals the limit as x approaches 3, f of x minus f of 3, 3, divided by x minus 3. So one of those, either one was fine with me, but I was looking for one of them. All right, now we go to part B. This is a problem you had no homework like it. I told you there would likely be something like that. So the key is to not panic. Let's just look at it carefully. So it says g is a function, and somehow we miraculously know its derivative. And then I want to find the value of this limit. So let me go back to what I hoped everyone would answer on part A. And of those that got it right, overwhelmingly, this was the form they used. It's what we did in class, not surprising. F of 3 plus h minus f of 3 divided by h. So the key for part B is to take a look at this limit and notice how similar it is to that limit. It's exactly the same limit. We're trading the function f for g. Part A is about generic function f. Part B is about a particular function g. And the 3's have been replaced with the 2. So if you got this answer for A, then you should just look at that and say, well, that's g prime of 2. That's the limit that defines g's derivative. And it's evaluated at 2. And miraculously, we know g prime's derivative. So we're going to plug it in, square it, plug it in down below, square it, and we get 4/5 as the answer. If you got A wrong, and a very common mistake on part A is not to tell me the definition. For those of you that made this mistake, you'll notice the word definition underlined in red. Like, we learned about the derivative. We wanted to get at some information, the slope of the tangent line. But what the derivative actually is determined by this limit. Okay? So there's a difference, and I think I wrote this on the board several times, at least twice, probably 3 or 4, that this is what the derivative is, and then there's what does that thing tell us? Okay, the reason why we care about that limit is because it tells us about the slope of the tangent line or the rate of change of the function, however you like to think about it. So we write the definition here. We notice that this is virtually identical to it, and here's our derivative miraculously. Don't know where it came from, but there it is, so ready for us to use. Now in part C, we want to find an equation of the tangent line. So to find an equation of any old line, what do we need? We need the slope and we need a point. The point is handed to us right there. When x equals 3, the function equals 4. The slope, well, we're talking about the function g, and we get the slope of the tangent line by the derivative, and there is the derivative sitting right there waiting for us to use. And so the slope, now notice x equals 3 here. So we're going to plug 3 in. We get 3 squared divided by 3 squared plus 1, 9/10. And now we can write our equation. Y minus 4 equals 9/10 times x minus 3. So there are our answers. So this problem illustrates something that students sometimes struggle with, and that is like how to do things versus why do we do them? Okay, so the why question here tells us, it relates to the derivative. The how, like, maybe you're thinking, I can compute derivatives all day long, I can get them right, no problem, but we need to know what it is. I mean, what exactly the derivative is, and that's where the definition comes into play. So we not only know how to do things, but we know why we do it. We know why the things we're working with lead to the results we hope to get. So I'll do the next question, and then we'll be done with this. So the next problem I want to talk about is number 6, sketching the graph of a derivative given the graph of the function. So we're told here that the function consists its graph of a line segment and a quarter circle. Hopefully the pictures convey that. And we want to sketch a graph of the derivative. I should say that each section had a different version of this graph. All of them were a quarter circle and a line, but the details varied. So this is the one for the 12 o'clock section. So let's find our identified points A, B, and C. So start with the easy part, the line from B to C. The derivative of a linear function, as we know, as we talked about in class, is just the slope. You can see the slope of this line. It's negative. It's going downhill from left to right. We don't really know the value. There are no measurements given to us on the axis, so we don't really know the value. But we know it's negative, and we know it's a constant. So I'm going to draw the derivative for that part sort of like that. Some negative number, and it doesn't change. And at B and C, we can certainly B is a point of non-differentiability. The derivative doesn't exist, and C is an endpoint. We don't really care there. Now, the quarter circle, notice that all the slopes are positive. Over here at A, now that line I drew, it kind of messes it up. But if you imagine this is a circle, I'll show you down here. Then on these endpoints, the tangent line, the tangents are vertical. And we know that when, as the slope approaches vertical, it gets bigger and bigger. Okay, and we know that when there is a vertical tangent, the derivative doesn't actually exist. So we have a derivative as we approach A. The slopes are all positive, and they increase actually without bound because we have a vertical tangent at the far side. So I'm going to sketch in an asymptote over here to help me draw that behavior. As we approach B, as we're moving around the circle like this, well, they could just keep getting flatter and flatter. In fact, at the very top of the circle, the tangent line is horizontal. So that has slope 0. So I'm going to circle in a point right here, and then the graph is going to do something like that, the graph of the derivative. So that conveys the information we know. I was really hopeful that the words here, the circle, we know what that means, vertical tangents at the ends, horizontal tangents at the top and bottom. That would help guide this. Now, it turns out I was pretty flexible in grading this. If you showed me a slope of 0 here and an increasing slope, maybe some people did something like this. They didn't quite realize that the slopes were approaching vertical as we approached that left-hand endpoint. But they knew they were getting steeper, so I gave that full credit as well. So let me go back to the right answer as best I can. Okay, so that's for the noon section. And like I said, the 8 o'clock and the 1 o'clock, it was just a variation. For some of you, the slope of the line was positive and the slope of the tangents on the circle were negative, but the concepts are the same. All right, that's number 6. Only worth 6 points, so it wasn't like a killer, but give you a chance to think creatively about the slopes.